Good day, everyone. We are Team Holmium, and we are to discuss about gravimetric methods of analysis. So let's start off with our topic outline. So here we are going to break down into different sections. First, we are going to discuss about the overview of gravimetry, which comprises of the principles and ideas behind gravimetry. And then next would be the different methods for gravimetric methods of analysis. So one of which is the precipitation gravimetry, volatilization gravimetry, and particulate gravimetry. So let's begin. Let me ask you this first. What comes to your mind when you hear the word gravimetry? Okay, I'll give you a few seconds to think about it. So I guess you have your ideas or thoughts that already formulated in your mind. So let's say if you think of the words such as weight, mass, weighing scale, weighing balance, analytical balance, precipitate, nucleation. So if you think of these particular words, I believe you're in the right track. So let's continue on with our overview of gravimetry. So gravimetry is any method to which the signal is a mass or a change in mass. So signal pertains to the result that we want to achieve in our, or we want the result that we want to use or achieve in our experiment. So to which we can obtain the mass by using a weighing scale. Here, the skill of weighing or the skill of weighing is crucial as we need to make sure about the materials we are weighing and how we do it. So shown below is the general procedure on how we are going to conduct a gravimetric analysis. So we start off with weighing our initial sample, and then if you want to form a precipitate, our sample should be diluted or should be dissolved rather in water. And then we are going to add certain reagents that can form a precipitate with our analyte. And then filtration or extraction will follow. And lastly, we are going to weigh our precipitate or our final sample using a weighing scale. So in conclusion, gravimetry is where we use the mass of our precipitate in determining the analyte in our sample. So let's go on with two ways of analysis or two methods of analysis with gravimetry. So one of which is direct analysis and the other is indirect analysis. So the only thing that we need to keep in mind is that direct analysis uses the precipitate that contains the analyte for weighing or to conduct our weighing. So which we are to weigh. So a good example of this one is determination of chloride in our sample with the help of silver nitrate. So silver nitrate or silver can react with our chlorine ions to precipitate silver chloride. Here, chloride can be determined from the material we use to weigh after the form of the precipitate. So that is direct analysis. As for the indirect analysis, we are to measure the change in mass that is due to loss or the mass of the compound form involving the analyte in a certain chemical reaction. So normally we are going to use a certain external condition such as heat to conduct a certain or to proceed with a certain chemical reaction. So a good example of this one is moisture content determination, to which we know the amount of water or the amount in grams of water in our sample when we expose our sample in heat. So first, we are going to, of course, weigh the sample initially and then expose it to heat at constant temperature for certain minutes or possibly certain hours until we reach a constant mass. So this constant mass can indicate that the majority of our water or what the majority of moisture content in our sample is already evaporated. And then afterwards, we weigh again the sample. And then we compute for the change in mass. And from there, we can determine how much water was removed from our sample. So here, the water is our analyte. So that is the difference between direct and indirect. So types of gravimetric methods, we have our precipitation method. So this is done to which the signal is the mass of the precipitate. So a good example of this one is lead content in determination in water. So this usually follows the solubility rules in which lead ions can be precipitate with the help of sulfates. So here, the lead sulfate or the precipitate is often weighed after the react or the chemical reaction to determine how much lead ions was there in our water sample. Of course, with the help of stoichiometry. And then volatilization gravimetry is where we use heat to remove any volatile materials from our sample. And here we can compute the change in mass to determine the amount of analyte that was present in our sample. So volatilization gravimetry is often called combustion analysis. As mentioned, that we using heat in the presence of oxygen to produce certain products. So here is an example of a simple setup uh, which in volatilization gravimetry. And lastly, we have our particulate gravimetry. So this is where the analyte is determined to which particulates are separated from the sample either through filtration or extraction methods. So other extraction methods can be also or can be adsorption methods. So that is one. So a good example of this one is determination of total suspended solids or TSS in water. So this can determine the amount of organic and or inorganic solids that is present in our wastewater. So this is very crucial in if we want to monitor the safety of our aquatic ecosystems as well as if we want to test its safety for drinking water. So particulate gravimetry is often utilized here. So importance of gravimetry. So here, as simple as it seems, right? We are just using mass as our signal in different experiments for gravimetry. So even it is simple as it seems, gravimetry heavily relies on stoichiometry and conservation of mass. So that's why it's very important to have the skills and knowledge when it comes to stoichiometry, as this is very crucial in this method of analysis. So this can aid in determining the amount of analyte that, of course, you are looking for. And also, results of an analysis are traceable. So here we can track down the amount of a certain compound or of a certain analyte with the use of gravimetry, as this is heavily reliant on fundamental physical properties such as
In precipitation gravimetry, an insoluble molecule is created when a precipitating reagent is added to a solution containing the analyte. It is due to a metathesis interaction. Precipitation gravimetric studies share two key characteristics. First, the precipitate must be low in solubility, highly pure, and known in composition. Second, the precipitate and reaction mixture must be easy to separate. Precipitation solubility is crucial for accurate results. Regulation of formation conditions and pH can reduce losses. Non-aqueous solvents can reduce solubility even if it is polar. Water stabilizes ions through solvation in aqueous solvents, so it is more soluble. We must also consider impurity removal from initial impure precipitates in dissolved solid solutions. To avoid determinate errors, we must remove coprecipitates. An inclusion, as seen in Figure A, is a common impurity where a potential interferent can substitute into the lattice structure if it precipitates with the same crystal structure. The probability of forming an inclusion is highest when the interfering ion concentrations is greater than the lattice ions. The inclusion mass is larger than expected and removal is difficult due to its chemical part. Reprecipitation is the only way to remove an inclusion. The one in Figure B is an occlusion. It forms when interfering ions are trapped within a precipitate, either along flaws or aggregates. It increases the precipitate's mass, but smaller, if it includes an analyte with lower molecular weight. Minimizing an occlusion involves maintaining the precipitate in equilibrium with its supernatant solution, known as digestion, which slows down the solution and precipitation rates. Surface adsorbents in Figure 3 attract ions from solution. Minimizing surface adsorbents can be achieved by decreasing the precipitate surface area, which can be achieved by digestive processes. Surface adsorbents can be removed by washing the precipitates because of its increase in size after digestion, but potential analyte loss must be considered. As for controlling particle size, it is crucial for precipitate formation, as larger particles are easier to filter and less likely to form surface adsorbents. Controlling reaction conditions can increase precipitate size, with larger particles formed when growth exceeds nucleation. There are also two well-known ways to filtering precipitate. Filter paper is a common method for separating precipitate from solution after digestion. Its speeds depend on its size and ash content on ignition. Filter paper is classified as fast, medium, or slow. Proper choice of filtering speed is crucial to retain precipitate and prevent clogging of pores. Too fast or slow filter paper can cause negative determinant errors. But among the well-known ways in filtering the precipitate, which one is better to use? Gravity filtration involves folding filter paper into a cone and placing it in a funnel. To seal, dampen the paper with water or supernatant, increasing filtration rate. Precipitate is transferred through decanting and rinsing until no precipitate is left in the beaker. A rubber policeman is used to transfer any clinging precipitate to the filter paper. Filtering a precipitate using a filtering crucible, such as a fritted glass crucible or a Gruch crucible, involves placing a glass fiber mat in the crucible to retain the precipitate. The supernatant is drawn through the crucible using a suction from a vacuum aspirator or pump, like filter paper, and the precipitate is transferred using the same method. So the answer is it depends. Both are equally effective, but using a vacuum makes the filtration faster. For rinsing and drying, separate the precipitate and dry it to remove residual traces and volatile impurities. The temperature and method depend on filtration method and precipitate's desired chemical form. Higher temperatures are needed for decomposition before weight determination. Quantitative applications require well-defined precipitates with volatile ions or hydrated water, which are typically dried at a temperature that eliminates these species, and non-stoichiometric solids also pose issues. This section discusses the determination of magnesium in water and wastewater using a precipitation gravimetric method. The method is based on method 3500 magnesium D in Standard Methods for the Examination of Water and Wastewater, 19th edition, American Public Health Association, 1995. However, this method is no longer listed as an approved method. Table 8.1 summarizes precipitation gravimetric methods for inorganic cations and anions. Most inorganic precipitants have poor selectivity for analytes, while many organic precipitants are selective for one or two inorganic ions. Precipitation gravimetric methods can determine organic functional groups or heteroatoms, with alkoxy functional groups being an indirect analysis. Stoichiometry of a precipitation reaction provides a mathematical relationship between an analyte and precipitate. However, knowing the stoichiometry isn't always enough for precipitation gravimetric methods. A conservation of mass can be used to deduce the relationship even without a complete set of balanced chemical reactions, as demonstrated in the single analyte analysis on the screen. Although qualitative applications have been replaced by spectroscopic methods, they still serve in spot testing for specific analytes despite their shift to quantitative measurements. The scale of operation for precipitation gravimetry is limited by balance sensitivity and sample availability, requiring at least 100 milligrams of precipitate for accuracy. Microanalytical balances are needed for trace level or microsamples. The accuracy of macro samples containing major analytes is typically 0.1 to 0.2%, with limitations due to solubility losses, precipitate impurities, and handling loss. Precision depends on sample size with 1 to 2 ppt for smaller amounts and several ppm for larger amounts, a level rarely achieved by other quantitative techniques. To enhance sensitivity, increase the molar mass ratio of the precipitate to the analyte, resulting in a precipitate with the largest formula weight and fewer analyte units. We can get the sensitivity by using the equation on the right side of the screen. Precipitants like silver are not selective for a single analyte, forming precipitates with bromide and iodide, posing a serious problem for accurate results. Precipitation gravimetry is a practical alternative for analyzing small samples due to its time-efficient nature, low equipment needs, and easy maintenance.
Another type of gravimetric method is volatilization gravimetry. Its name stems from the reason that this type of analysis typically produces volatile products through thermal or chemical decomposition of the samples. Quantitative information from volatilization gravimetry can either be obtained from trapping and weighing the volatile products or by weighing the residue of the sample after heating. In this type of gravimetry, it is important to know that the products of the decomposition reaction. While it is common for organic compounds to produce simple gases like carbon dioxide, water vapor, and nitrogen gases, inorganic compounds often depends on the temperature to determine its thermal decomposition products. One method to determine the products of thermal decomposition is through thermogravimetry. This product involves monitoring of change in the sample's mass as a function of temperature, and with the use of a thermogram, the loss of a volatile product can be visualized. A thermogram, as shown in this slide, is a graph which shows the mass as a function of the applied temperature. A step in a thermogram refers to the change of mass in response with the applied temperature. This can be more understood with the use of an example. Let us try to answer this sample problem. The original sample weighed 24.60 milligrams and was heated from room temperature to 1000 degrees Celsius at a rate of 5 degrees Celsius per minute. The following changes in mass and corresponding temperature ranges were observed. A loss of 3.03 milligrams from 100 to 250 degrees Celsius, a loss of 4.72 milligrams from 400 to 500 degrees Celsius, and a loss of 7.41 milligrams from 700 to 850 degrees Celsius. The problem asks to determine the volatilization products and solid residues at each step of the thermal decomposition. First, let's address the loss of 3.03 milligrams from 100 to 250 degrees Celsius. Given the original mass of sample, 24.60 milligrams, we will address the loss of 3.03 milligrams from 100 to 250 degrees Celsius. Let us first get the percentage of the lost mass by dividing it to the original mass and multiplying it to 100. There is a loss of 12.32%, which you can also see in this thermogram, and we'll consider it as the first step. To determine the compound loss, we will then multiply it to the molar mass of the sample, calcium oxalate monohydrate, which is 146.11 grams per mole. The 18 grams per mole can be accounted for the loss of water vapor, as it accurately corresponds to its molar mass. Removing the chemical formula of water in the original sample, we will get a residue of calcium oxalate. Moving on, we will address the loss of 4.72 milligrams from 400 to 500 degrees Celsius. Applying the same step, we will get a 19.19% loss of mass in the sample upon heating at 400 to 500 degrees Celsius. This is the second step, which you can also see at the thermogram. Using the molar mass of the sample again, we will get a molar mass of 28.04 grams per mole. The molar mass corresponds to the molar mass of carbon monoxide. Thus, we will consider it as our gas product. Following the same step from earlier, we will get a residue of calcium carbonate. Lastly, we will address the loss of 7.41 milligrams from 700 to 850 degrees Celsius. Here, we will get a 30.12% loss of mass in the sample upon heating at 700 to 850 degrees Celsius. This is the third step, which can also be seen in the thermogram. A molar mass of 44.01 gram per mole can be calculated using the percentage. This value corresponds to the molar mass of carbon dioxide, and thus we will consider it as our gas product. Following the steps earlier, we will get a residue of calcium oxide. Just a recap, in our sample problem, three steps of thermal decomposition were utilized to determine the products by heating calcium oxalate monohydrate at the temperature at the temperature range of 100 to 250 degrees Celsius. A loss of water vapor and a residue of calcium oxalate can be observed. On the other hand, at a temperature range of 400 to 500 degrees Celsius, loss of carbon monoxide and a residue of calcium carbonate can be observed. And lastly, at a temperature range of 700 to 850 degrees Celsius, loss of carbon dioxide and residue of calcium oxide can be observed. The information we obtained in gravimetry are useful in creating a strategic analytical method. If we want a residue of calcium carbonate, we now know that we must treat the sample at a temperature range of 400 to 500 degrees Celsius. Equipment used in volatilization gravimetry can vary from simple to more complex setups. With a simple experimental design, the composition of the sample can take place with the use of a burner, lab oven, or a furnace, and its residue can be weighed using an analytical balance. However, on more complex experimental design, the thermal decomposition of the sample must take place at a closed container wherein inert purge gas stream will sweep the volatile products to several selective absorbent drums. Lastly, a typical thermogravimetric analysis uses an electric furnace and electromagnetic balance. The sample will be placed in a small balance pan, which is connected to the electromagnetic balance. The instrument includes a gas line for purging the volatile decomposition products out of the furnace and a heat exchanger to dissipate the heat emitted by the furnace. The thermocouple is used to monitor the temperature. Volatilization gravimetry plays a crucial role in chemical analysis. In fact, it has a wide variety of applications both in inorganic and organic analysis. For inorganic analysis, here are some of its useful applications. Applications include ash content determination, dissolved solids determination, and moisture determination. For organic analysis, applications include elemental analysis, alkaline metal determination, and biomass determination.
In the previous lectures, we saw that different types of gravimetry require the conversion of the analyte from one form to another that is easier to weigh. But what if the analyte can readily be separated from the matrix? Particulate gravimetry refers to the separation and quantification of an analyte readily available for separation. A particulate, by definition, is a tiny portion of matter suspended in solution or in the air. Particulate gravimetric methods heavily rely on the weighing equipment it uses, hence, its selectivity depends on the sensitivity of the balance. Generally, particulate gravimetry requires less time, labor, and capital since it only employs separation techniques before quantification. One separation technique commonly used for particulate gravimetry is filtration. Filtration can be as simple as using filter paper to separate solid particulate matter from a liquid matrix. Other filtration methods use pressure to suck out the liquid from the solid analyte. The smaller the filter's pores, the better the particle retention. Particulates suspended in gaseous matrices can be filtered with filtering media used for liquid samples, while solid samples are filtered by sieves of different sizes. This method is analogous to sifting flour. Extraction may also be used to separate poorly filterable solids. The matrix is first dissolved in a suitable solvent to extract the target compound, then the solvent is evaporated before weighing the sample's mass. Adsorption can also be used to extract poorly filterable solids from a gaseous or liquid matrix. One such example is the adsorption of carbon dioxide from the air by activated carbon. The problem with adsorption methods is that the sample cannot be quantified with conventional weighing instruments such as the analytical balance. Usually, a special weighing equipment is used like the quartz crystal microbalance, where a change in the resonant frequency corresponds to the binding of an analyte to the adsorbing material. Different industries utilize particulate gravimetry for their analyses. These include the microbiological testing of water, determination of crude fat content in chocolate, and the analysis of gaseous pollutants in air. To summarize, gravimetry is a simple yet powerful technique that is still used for a variety of analytical tests. Thus, it is essential for learners of chemistry to understand how it works and to which types of analysis it applies to. For more information, please read Harvey's Modern Analytical Chemistry. Thank you for listening and have a good day.